It's a great honor to present at EGF MedFract conference here at Catania. My name is Guowei Jiang. I'm a PhD student in Politecnico di Milano. My supervisors are Laura Vergani and Federica Buccino. First, I'd like to give a brief introduction of my background. Vertebral fractures are common and clinically important problems, especially among elder adults and people with osteoporosis and those with low bone densities. They can result from everyday low energy events like a fall from standing height when your bone is fragile, or a major trauma like traffic accidents. Clinically, it can result chronic pain, reduced mobility, and loss of height, and impaired quality of life. It can also increase the need for hospital care and long-term support. My colleagues' previous study established a novel setup and a multifunctional in situ testing system for imaging-guided failure assessment of biological materials, for example, woods and bones, and it's using synchrotron radiation-based micro CTs, and this system enables us to do microtensions, microcompressions, and metal torsion tests under displacement and the rotations with controlled angles. It can also produce real-time four-dimensional images of microstructural damaging evolution under mechanical loadings. So all the specimens of lumbar discs used in this study were obtained from patients with lytic metastasis disease under ethically approved donation program. So all the samples were cutted into cuboids and then glued into 3D printed end cups and then loaded to this system and underwent torsional loading. All the samples were twisted up to 10 degrees, applied in steps of 1 degree. The rotations rate was set to 1.8 degree per second, and 30 seconds relaxation between steps were applied. And the samples were scanned by the synchrotron at each step after a relaxation. So thanks to the high resolution of synchrotron images, we're able to not only to see the regional, the common structure of bones, but also the microstructure of cubicular bones, the lacunas, and even the micro cracks initiatives. So we find out that the local reductions in relatively density can be linked to early stage mechanical weakening. By analyzing the images, we also find that there was significant intersample differences in shear stress measured at equivalent strains. So it caught our attention. What causes the difference between samples? At the macroscopically level, the difference in trabecular bones structures like the distribution, the orientation, and the morphology may alter the bone mechanical response. And this structural difference may result in or may reflect the lifelong patterns of loading or unloading. In other words, it may reflect how physically active or sedentary somebody has been for many years. So this motivated us, the focus of our epidemiological studies on long-term behaviors. Sedentary behavior is common and increasing. Surveys estimated over 60% of adults has sit more than 7 hours per day worldwide, but the number is still rising with increased office work, commuting, and digital device use. And also these patterns are differ by the age, region, and the occupation. Older people and the people with desk use the jobs may sit more. So here we can categorize the peoples with 4 categories, like physically inactive or physically active, high sedentary or slightly sedentary. The prolonged sitting has multi-system effects. Epidemiological studies have consistently linked the high sedentary time to a cardiometabolic disease, for example, type 2 diabetes, obesity, and also heart disease, and to overall higher mortalities. And they also have associations with worse mental health outcomes, like higher rate of depression symptoms and poor well-being. From musculoskeletal perspectives, it may reduce the muscle strength and endurance, and alter the spinal loadings, and finally contributing to chronic low back pain and may potentially accelerating the bone loss. Functionally, inactivity may harms the balance and mobility, increase the fall and fracture risk, and reduce the independence in older adults. But it's still hard for us to draw a conclusion that higher sedentary time results in the higher risk of bone fractures. Why? Because the observation studies have limitations on causal inference. Confoundings like lifestyles, socioeconomic status may bias the associations. Reverse causation here is a particular problem because the early spinal pain or vertebral disease may cause reduced activity and may creating misleading associations. Measure errors is common, and especially when the activity and sedentary time are self-reported. Selection bias, for example, the healthier volunteers may be overrepresented, and the residue and unmeasured confoundings may still remain even after the adjustment. So that's how the classic epidemiological study draw a conclusion. After we obtain the observed association, we need to exclude the random errors, spurious association, and confoundings to finally draw a causal association. All these challenges lead us to adopt the Mendelian randomization to strengthen our causal association. Before explain Mendelian randomization, I want to recall our audience the memory of Mendel's law of segregation. This classic Pease experiment demonstrated very well. So during gamete formation, the parental alleles were randomly passed to their offsprings. So they will generate very predictable possibilities. So the main idea of Mendelian randomization is the genotype of an individual's genotype is fixed at the conception, and therefore will proceed with the exposure and the outcomes. So when a genetic variance, also called SNP here, is associated with a reliable exposure, can then serve as an instrumental variance to effectively allocate people to different lifelong exposure levels to in a manner as a randomization in a trial. Why? Because genotypes is very generally independent to most of the confounders and cannot be changed by the outcomes. So Mendelian randomization uses these genetic instruments to reduce confoundings and rule out reverse causation. Here, my hypothesis was very simple. Greater lifetime physical activity reduces the spinal fracture risk, while greater lifetime sedentary behaviors increases. Our exposure in this study is sedentary time and also physical activity. The outcomes will be spinal fractures. The SNPs here are the genes that make people are more likely to sit more or to do sports. We obtained our accelerometer measured data from UK Biobank and also the outcome data from population cohorts. And this slides this LIV1 out sensitivity analysis shows each black dots represents a Mendelian randomization estimated obtained when one SNP is excluded. The red dot and the line at the bottom shows the overall estimate with all the SNPs. As you can see from this picture, all the excluding any of the single SNP produce a minimal change in the overall estimate. So it means no individual SNPs drive the overall inference, which supports the robustness of our Mendelian randomization carrier inference. This final plot accesses the directional pleiotropy of this study. Each point represents the SNP-specific Mendelian randomization estimate. And as you can see from this picture, the points are roughly symmetrically distributed in the two sides of these two lines. These are MR-Eager and the LVW line. And these two methods are very close to each other, which means there is no evidence of directional pleiotropy. And I made a mistake on the title page of this slides, but when I find out, I already submit the PowerPoint. So please allow me to orally correct it. The title should be the SNP's effect. So as you can see here, each dot presents per SNP's effect on exposure against per SNP's effect on outcome. With the fitted line of all the three methods estimators. So these three methods show a consistent and positive trend, and it should be emphasized that no single SNP is a clear outlier that's driving the result. So here we can finally draw a conclusion that sedentary time and the spinal fracture risks are positively correlated. Moving forward, for the next step, we are planning to further validate our results with experiments. So we will continue collecting samples by the patients with contrasting profiles with highly sedentary versus physically active. And then we will apply imaging guided failure assessment to the lacunas distribution, morphology, and orientation in our samples. And finally, we can link our epidemiological study results to the measurable biomechanical differences. To summarize, our Mendelian randomization studies find evidence that higher overall physical activity is causally associated with low spinal fracture risk, and greater sedentary time is linked to higher risk, while vigorous activity shows a consistent protective signal. So for the public health implication, it's very straightforward. Promoting activity and reducing sedentary time could help prevent the spinal injuries. Finally, I would like to acknowledge this research was supported by the GAP project funded by the European Union's Horizon Europe Research and Innovation Program under the Mary Sklodowska-Curie Action. Thank you for your attention.